Lyme disease is the most common arthropod-borne illness in the United States, infecting almost 500,000 people every year. Lyme disease is caused by spirochete Borrelia burgdorferi and is transmitted to humans via black-legged tick bites. Early symptoms include fever, headache, and the infamous bull's eye rash. As the disease progresses, 1 in 4 patients develop Lyme arthritis, and 60% experience joint swelling unless treated with antibiotics. If left untreated, the disease can progress onto the nervous or cardiovascular systems, causing facial palsy or carditis. For such a menacing disease, treatments are concerningly limited. No preventative vaccines exist, and symptoms often persist after treatment. As such, further disease research is needed to help mitigate the long-term damage of Lyme disease and to limit the suffering of millions of people worldwide. To treat Lyme disease, we must first understand how Borrelia causes the disease on a molecular level. Recent studies show that Borrelia secretes nucleotide-based cyclic di-AMP molecules, which bind and activate the host's innate immune receptor sting, thereby inducing a type 1 interferon response and thus sustained inflammation. Borrelia secreted cyclic di-AMP molecules are produced by the DisA protein, a diadenylate cyclase that uses ATP to synthesize the molecule. Homologs of this protein have been studied in other species, but its structure and function in Borrelia remain largely unexplored. This is where my project comes in. I'm working to solve the crystal structure of the Borrelia DisA protein to enable novel pharmacological targets to treat Lyme disease. Inhibiting Borrelia DisA could dampen cyclic di-AMP signaling, reduce sting-mediated inflammation, and ultimately address the chronic inflammation associated with Lyme disease. So far, I've cloned plasmids carrying the full-length and truncated versions of the protein, transformed and expressed them in E. coli, and purified them via nickel affinity and size exclusion chromatography. The SASPage gel electrophoresis confirmed the protein identity in the elution, while the size exclusion data show that Borrelia DisA elutes as a dimer, which is consistent with the other DisA homologs. After purification, I moved on to X-ray crystallography. I set hanging drop trays in around 500 conditions at varying protein concentrations and incubation temperatures. At a protein concentration of 15 milligrams per milliliter, I observed 3 conditions that form small needle-like crystal hits. My next steps are to refine these conditions to form larger, more uniform crystals. These optimized crystals will be sent to the synchrotron for X-ray diffraction data collection. This data will allow me to solve the structure of DisA and characterize active site residues, catalytic mechanisms, and potential binding pockets. Overall, this research will lay the foundation for novel targeted therapeutics to attenuate Borrelia-mediated inflammation and immune activation. Thank you.